The third talk in this session will be by Raúl López on symbolic analysis by using folding narrowing with irreducibility and SMT constraints.
Okay, thank you. So I'm starting with this presentation. This is the outline. First we will have an introduction. Then I have prepared a narrowing example so we can understand a bit what narrowing does. Then we have the running example, which is the base of the running example is coming from an example which was presented here last year. Actually, some of the authors are here present. Then we are seeing our folding canonical narrowing with irreducibility and SMT constraints. I have some execution examples and finally the conclusions. So let's start. Okay, rewriting with Satisfiability Modulo Theories has been recently used to analyze system modeled using Parametric Timed Automata. Okay, we are no experts on parametric time automatas, but we have used those examples to show the potential of our algorithm. Okay, so in this work, we propose to generate a finite state graph, not by rewriting with SMT, but by narrowing with SMT. Narrowing with SMT allows a greater generalization. For example, an infinite number of initial states may be represented by a finite number of states with variables, and not only the SMT variables. Everything can be a variable in narrowing. An infinite state graph from an initial state may also be represented by a finite state graph from another initial state with variables. We use graph search pruning techniques via irreducible terms, would come from previous work, and SMT constraints on conditional rules. Okay, so why extend narrowing algorithms? Our implementation of folding SMT canonical narrowing really generalized, as I said, previous techniques for symbolic analysis as rewriting. With our symbolic reachability algorithm, not only numeric variables can be found in the initial and final states, but variables of other types are also allowed. Now, if we check a property using reachability problems with variables, then we are checking it for all possible instances of a problem, okay? So if we have a generic initial state and a generic final state, and we verified a property using narrowing, then all instances are covered. For our algorithms and for the experiments, we use the mod system. It's a system and a language based on rewriting logic, so it uses both rewriting rules and equation, and it is capable of handling many forms of symbolic reasonings, such unification, narrowing, most general variant unifiers, and SMT. Currently, it's used in a wide spectrum of areas, like security protocol analysis. Santiago, the co-author of this work, does that a lot. Then through model checking, partial evaluation, theorem proving. But there are some limitations of narrowing in mod, which can be, for example, handling conditional theories or handling SMT constraints, irreducibility constraints, etc. And we have made some extensions of narrowing in mod. The first one was to add the canonical narrowing to the standard algorithm. So we used irreducibility constraints to make a pruning of the tree and reduce the search space. Then we had the addition of SMT constraints. So we handle conditional theories, which contains SMT constraints in the conditions. And then in this one, we combined those two articles into one, and use it to define a lot of experiments and some practice. And also we have in ICFEM 2022 another line, let's see it like that, in which we handle conditional rewrite theories, but not only with SMT in conditions, but with variant conditions. And now in this work, we are using the canonical narrowing with SMT constraints, but now we have the folding narrowing. Okay, so the folding narrowing what does is folding the search space, so we can, well, we see later. Okay, but let's see first an example so we can understand how narrowing works. This example is just a basic coffee machine. Okay, I will not. Sorry. I will not explain in detail because I don't have any much time. But basically, we have two rules. Okay, they model the transitions of the system. So in the first one, we can just take $1 and buy a coffee, and in the second one, we can buy an apple, and a quarter of $1 is left over. Then we have some equations that are just equalities. The first one is an equation of change. 4/4 of $1 become $1. And then we have three idempotence equations, one for each symbol, okay, but not for the quarter because we already have a equation saying that 4/4 of $1 become $1. So we have idempotence for apples, coffees, and dollars. It's a little counterintuitive to have idempotence on money, but it's just for showing how narrowing works. Okay. This is an example of how we can visualize an execution of narrowing. So imagine we have an initial state M1, which is of type money, and then we have several transitions that we can do. Then we will have several branches on the search space. Okay, so some of them are not deployed here because of the space of the slide, but we are interested in this one, the red one. Okay, and we can see it with some detail. So we have the initial state M1, and then we want to do the first step, and that could be applying the second rule to buy an apple. Then we have a substitution for the variable M1, which says M1 becomes $1 and another variable M2 of type money. And then we have another substitution for the variable of the left-hand side of the rule, so they can both unify M1 and the left-hand side of the rule. We rename it because of mod purposes, so M becomes W1 and it becomes $, and M2. Then, if you see in detail, we have now $2 in the left-hand side of the rule. Okay, we have $1 and the dollar of the substitution, so we have $2 and M2, and here M1 is only $1, but because of the idempotence equation, $2 become 1, so these $2 will become 1 and unify with the M1 variable. Okay, now we can make the step, take the step, sorry, and we go to this state. Since M1 is $, M2, we get $1, an apple, a quarter left over, and M2. We can go to the next step, and it's pretty the same. Okay, so now we apply the first rule to buy a coffee. Again, we have the 2 substitution, and again, we use the idempotence dollar equation, and we go to the third step. In the third step, we apply again the second rule to buy an apple, and again we have the two substitution. We apply the idempotence dollar equation, and this is a narrowing trace, okay? A normal narrowing trace. What happens here? In the first step, we use the second rule, but we could also have used the first rule, so that would be another different trace, and that happens in every step. So in the end, we have something like that, like we saw before, like a big tree with a big search tree, which actually in this example is infinite, since we are using a generic variable M1, and the system can always introduce a new variable of type money. Now we have the running example. As I said, this is coming from a paper presented here last year. So basically, it's a coffee machine presented as a PTA. First of all, we have the idle state, and the system can be there for an arbitrary time. When the user presses the B start button, the counters x1 and x2 are reset or initialized, and we go to the state add sugar. In this transition is modeled in mode with something like that. Okay, it's a conditional rule. This is not the original rule. Okay, it's slightly modified, so we can use it with narrowing, but the original rule is quite similar. We have the state, the two counters, and the parameters, and we go from idle state to add sugar state with a new value for the counters and the same parameters, and with the SMT conditions modeling the initialization of counters and this invariant. So the system will be here as long as the invariant holds, and in this time the user can use the button B sugar to add some sugar. If x1 is greater or equal than the parameter p1, and the counter is reset. After p2 time, p2 time after the B start button was pressed by the user, a cup is delivered, and we go to the preparing coffee state, and we will be there as long as x2 is less or equal than p3, so that's a new invariant. And finally, after p3 time, since the after the user presses the B start button, the system delivers a coffee. Sorry, this one. The system delivers a coffee, and the x1 counter is reset again. We go to the final state, done, and we will be there 10 unit times, unless the user presses again the B start button, and we start again in the add sugar state. Now, our extended or modified version of the PTA, I don't know if someone here is an expert on PTAs, and we are not sure that this could be actually considered as a PTA, but it's just an example to show what we can do. So now we add two new variables. The first one, C, will be a counter of coffees. So now we have a count of the coffees prepared. And the second one is just like in the example before. the money. So now we have money. And actually, in the idle state, we have a new transition, B quarter, what we call B quarter, but it's not really a button. It's just that the user can introduce quarters of a dollar to the total amount of money. And to go from idle to add sugar, we need 3/4 of a dollar. So a coffee costs 3/4 of a dollar. The same happens when we want to go from done to add, this one is from idle to add sugar. And the same happens when we want to go from done to add sugar. If there are 3/4 of a dollar left, we can make another coffee. And from preparing coffee to done, we add a coffee to the counter of coffees prepared. So as you can see, the rule is quite similar, but now we have here the money and the counter of coffees. And in this transition, the B-star transition, we can see how we have at least 3/4 of a dollar and the rest of the money. And to take the step, we take out the 3/4 of a dollar. Now, folding or narrowing in mod.
Some question.
Mm-hmm.
Just clarification. Okay. Some simple question for just clarification to understand example. So I guess that basically this M contains multiset of Q.
Which?
There's the new components contain multiset of these Qs, right? So,
Yes.
So is there any reason that you do not use integer?
We did not use what?
Integer theory of integer to encode the number of Q. So
of integer. Yeah.
yeah.
Because
So just curious. Then there would be pure.
yes. So sorry. Yes.
SMT.
That's a good question because I missed that. So the idea is that we also wanted to have equations in this system. So by having quarters of a dollar, we can also have the equation that we saw before, in which 4/4 of a dollar become a dollar. So we can have change of money in that way, and that's only the reason. Okay, so now to follow narrowing in mod, we have the data structure which was a tree, and now it has to become a graph since we are folding the tree. The data structures of the nodes must also be modified to include new information, for example, the node on which it's fold or not. And we have to add new functions to determine when a node falls into another one. And it should be checked bidirectionally for nodes of the same depth. So a node which is on the same depth of other nodes, they can fold bidirectionally, okay? So if one doesn't fold into the other, we have to check it the other way. We make several calls to mod's SMT solver to determine if the necessary implications are satisfied. And actually, in a future, I'd like to maybe try the Q-mean version of mods, so we can use other SMT solvers, because we are only using now the JSys2, I think is the one mods uses. So when does a node fall into another? Nodes are now a triple composed by a term, an SMT constraint, and a list of irreducibility terms. And a node falls into another node if the first node is an instant, or the first term of the node is an instant of the second term. That means that exists a substitution, and applying that substitution to the second term and modulo equation and actions, it becomes T1. The second condition is that implication, the negation of that implication is unsatisfiable, that means that we are checking the validity of the implication. And the last condition is that the terms in the term in which we apply the substitution, T2, so the terms in the irreducibility list of 2 must be EV irreducible. That means modulo equation and axioms. Some example of executions. I don't know how I'm going with time. I'm fine. Yeah. Okay. So, for example, this one is, I think it's quite similar to the one used in the original work, but using narrowing. So we can ask, is there a way to get from a generic idle state to the done state by buying at least 3 coffees and with at least $2 left over? Note that we can use at least because we are using a variable next to the $2 and a variable next to the 3 coffees. So it is at least, not exactly 3 coffees and $2. And if we don't use folding, the execution will be stuck in an infinite calculation. Why that happens? Okay, that happens because if you check the model, the system can always go in one of the traces from the state done to the state at sugar by B start, by transition B start. So there is a loop, and the narrowing without folding won't be able to terminate. But if we use folding, folding will achieve something similar to the system model. So it's folded, and then it can find a solution. So the answer to the question is yes, we can do it. Another question, is there a way to get from the idle state to the done state by giving any values to the counters, the parameters, money and coffee? So it's the same, it's the same as before, but now everything is a variable. So this is just like going from a generic, completely generic initial state to a completely generic final state. And again, a solution is found. So the answer is yes. And the last one, what if we start with exactly $2 in the idle state? Then we will have 2 different solutions. Why? Because the first one will be that we buy 1 coffee and $1.25 left over, and the second one, with the first one, we go from done to idle directly, and the second one, there will be only a loop, and then we buy 2 coffees and $0.25 left over. And the conclusions. So we have developed a novel folding SMT canonical narrowing, which extends our previous works. These narrowing techniques use both irreducibility constraints and SMT constraints. The SMT constraints will be specified within the conditional rules, and the irreducibility constraints will help to reduce the width of the search tree when using rewriting theories with complex varying unification. In this case, the impact of canonical narrowing, that is the impact of irreducibility constraints, was not too much, but in cases in which we have a lot of equations, the difference between standard and canonical narrowing is huge. Folding can considerably reduce the computing time or as we saw in examples, even ensure termination, when the search tree can be fully folded into a finite search graph. And we have used the algorithm to analyze a PTA vending machine that was specified and analyzed with rewriting modulo SMT. We have also extended the example with new features to further demonstrate the symbolic potential of the algorithm. And we think narrowing goes a step further at the symbolic level, allowing us to use variables beyond SMT in the initial terms. And that's all. You can find both the code and the implementation of the algorithm in this link. And yeah, that's all.
I have two questions. First, what makes you believe, you mentioned it, that the parameterized timed automaton is not one actually, and the second one is perhaps so the automaton you said the automaton you have in front of you is perhaps not actually a parameterized timed. Okay. What is the reason why it is not a timed automaton?
No. I said I don't really know, since I'm no expert in parametric time automata. I don't know which are the restrictions to consider a parametric time automata as that.
Well, I mean, you see here all the new stuff, right? So because in time automata, you can only the clocks can only be set to 0, right? So everything that's new here, I mean, it's not part of the definition of an automata or time automata. So
okay.
It's M is assigned to M minus Q to Q. I mean, it's not just a part.
Thanks. That's what I was wondering. Okay, and the second one is maybe I was missing the misunderstanding the folding and the role of the folding. But if you hide non-termination cases, is this folding then sound?
Yes, I don't really know the theoretical implications, but the answer is yes.
Well, I mean, you do exhaustive state analysis if you find the same state again or something like that. So then,
well, okay. So then maybe since I'm here, I can have also some questions. I got the mic. So I guess, I was just confused with the first example, right? That $1 became $2 or vice versa, but that of course doesn't apply here, right? So or quarters and so on. The second example, but the main issue is, which I noticed that in the first example was a little bit artificial because you used the global rules. I mean, so the left-hand side have to somehow seems like it catches the entire state.
You mean this one?
Yeah. So you see, normally, I mean, normal example would just be by C would be $, goes to a coffee, right? So without the M and without this
Yes.
angled brackets, right? So can you tell me more about that? Is this necessary? I mean, your approach only works on these global rules.
No, I mean, if we remove the variable from the rules, we would be doing rewriting.
Yeah.
So we could use narrowing, but the solution will be equivalent to that with rewriting. So the idea is to have something a bit more generic.
Okay, so you need that in the rules to be able to do this narrowing.
Yes.
Sure. Okay.
I mean,
then it's a little bit less valuable, right? Because then you have to first fake the rules in some sense.
Yes and no. I mean, it's just a modification of the model, so you can have something more generic.
Yeah, but as an engineer, I mean, as a developer system, I would just write, $, goes to C, right? I mean,
yeah, but yeah. Shall I?
Comments and also question. Some comments. It's necessary because narrowing-based analysis will not be complete if the rule is not topmost. So should be topmost, otherwise incomplete. And then another question. Some question is that it seems that narrowing should not involve any SMT variable, right? So somehow you assume that states is separated.
Yes.
Some parts only involve narrowing and some part only involve
Yes.
SMT. Do you consider some mixture? Or
Mix them.
Yeah, mixing some SMT constraint.
Yes, I mean,
narrowing.
not.
Yeah, just some.
We can't handle that now, but we are thinking about some ways of handling it. So yeah, maybe we can do it. Like we have it on the list of future work.
It's more interesting because, for example, I guess that for the next example of that involves a number of different components of timed automaton, right? So in that case, each timed automaton component involves some clock variable, and then considering arbitrary number of components should involve mixed data structure containing both SMT variable and narrowing list. So it might be more interesting.
Yeah. We think it's quite interesting that approach, and we really thought about that, and we will think about that much more because as you said, it's really interesting and could be way useful.
Any more questions before lunch? Okay, then let's thank the speaker again.